Hi, in today's video, let's take a look at this microwave transceiver. This kind of transceivers are commonly used in detecting moving objects. Since it is using the Doppler effect, it can also detect the velocity of the moving objects. This particular one is from Microsemi's MDU 1020 series, and according to the datasheet, it is operated at 10.5 gigahertz. So here is the datasheet, and you can see that the possible applications include intrusion alarms, and speed measurement, and collision avoidance, traffic control, etc. So this particular one is operated at 10.55 gigahertz, and there's some detailed datasheets here. So anyway, so let's take a look at, from a high level, how this microwave transceiver works. So actually the theory of operation is quite simple. We have a local oscillator here. So this is typically the frequency at which it operates. So in this case it is, let's just say 10.5 gigahertz. And then we have an output antenna. So the signal goes out and bounces back from an object somewhere. And it comes into a receiving antenna. So this frequency, so let's call this F0, and the frequency coming back is F1. So it gets either amplified or just directly coupled into a mixer. It mixes with the original LO, comes out with this frequency beat, which is the delta F equals the difference between F1 minus F0. So that's our Doppler frequency. For those who are familiar with how Doppler frequency corresponds to the speed, and we can easily derive the v at which the object is moving. The v, let's move the paper up a little bit. So the delta v equals the delta f we measured over f0, which is our base frequency, times the speed of light. So using this equation, we can actually calculate how fast the object was moving. And before I take it apart, I just want to briefly demonstrate how this thing works. Okay, so here's our setup. The noise you hear in the background is the spectral analyzer, which I will show you guys a little bit later. But here we have powered it up with plus 5 volts, and the white lead here is the IF output, so corresponds to what we just saw here. Okay, so that's where the delta F is going to be outputting, and so that goes directly to the oscilloscope. And right now, as you can see, when we are not moving, there's nothing going on. But if I wave my hand in front of the sensor, you will see some wave showing on the oscilloscope. Now the frequency of which is directly correlated to how fast I'm moving. So for example, if I use a ruler to rapidly oscillate in front of the sensor, then you can see that the frequency actually showing on the oscilloscope is much higher than versus I just move my hand gradually down like this. So this is in principle, the Doppler effect, how it works. Now, also I have up here is the spectral analyzer. So I just want to show you the frequency at which it operates. So right now, let's zoom it in. Let's actually put the center frequency to 10.55 gigahertz. And let's do a frequency span of 100 megahertz. So you can see our signal. Let me center it a little bit. So let me center it. So that signal is actually what is sending out from the Doppler sensor, and basically that signal bounces back and get mixed with the itself actually. So that's a frequency shifted version of itself. So to prove that, well, not to prove it, but to show that in a little bit more detail, I also have this WaveTech microwave generator up here. So what I'm going to do is I'm going to set it up to generate a tone that is roughly the same as the frequency that this microwave is operating on. So for that, I'm going to change it back to the view of the spectrum analyzer, so you can see the tone coming in. So when it's warming up, it will shift a little bit. But so watch what happens when I move that tone very close to the actual oscillator frequency. So I want you to watch on the oscilloscope. I'm going to gradually increase it. Oops, this is very sensitive, so now I'm going to gradually decrease it. So you can see that, hang on just 1 second, let me, as you can see, when this overlaps, you can see the beat frequency on the oscilloscope down there. So clearly this is the mixer output. So I wanted to show you this because I just want to make sure that we understand this is actually from the mixer output, this delta F. So it's directly a difference between the transmitted wave and the reflected wave. Okay, so now let me turn off the noisy spectral analyzer, and we can open it up and take a look at what is inside. Before I take it apart, I just want to show you the back. As you can see, this one is actually has UK patents for this particular construction. So I'm eager to see what is inside. And just from looking around, there's no screws. So I think all we need to do is just pry these clips open, and we should be able to get in. So give me a moment, I'll be right back. And it's pretty difficult to open it without destroying the case, but I opened it, and so as you can see, the construction is actually indeed as what we expected. So here is the top, and inside we seem to have a very soft piece of metal, which is RF gasket. And let's put it aside. And then we have the main circuit board. So this board actually comes out like that, and you can see that we have nicely RF the compartments for different portions of the circuitry, and there's a piece of absorbing material, and this screw actually, so it's coming from the back here. I forgot to mention is that you can actually turn this screw to adjust the operating frequency a little bit. I think it's a little over maybe a couple hundred megahertz over the 10.5 gigahertz center frequency. So now we can see what really is inside. Actually, this looks surprisingly similar to one of the modules that I actually saw it on, I believe on some forums, that somebody did a teardown of the HBM 100, I believe that was. And that was a Chinese-made module. So hold on, let me actually see if I can find that picture, and we will take a look. Okay, so yep, indeed. So I actually just printed out a the other module, which is a HBM 100. Now, my printer is a little bit of, I think the printer head is a little bit dirty, so, but you can actually see the construction is surprisingly similar to what we have here. So clearly, in fact, some of these features are almost exactly identical to what we have here. For example, these filters towards the main oscillator here, as you can see, except for the direction is different, but the arrangement actually are exactly the same. So I'm wondering if there's any patent infringement or not, because after all, this design is based on UK patents. But of course, these cheap Chinese knockoffs don't, I guess they don't care about the patents at all. Anyway, so the first thing you look at this is actually the construction. Surprisingly, it's a very, very simple. It only has 1, 2, 3, 4, 5 components. And besides these two active components, which I assume this is the main oscillator transistor, and this is the mixer transistor. And you can see we only have about 3 passive components. So let's take a quick look at how this thing works. So up towards the top, you see this single microwave transistor, which is either a bipolar transistor or a field effect transistor. And it basically is the main local oscillator. Now, if you look carefully, you will see that this cylindrical component is actually not connected to anything. So this is actually, for those who are familiar with microwave components, this is a dielectric oscillator, resonance oscillator. So it has an extremely high Q value. So basically, based on the dimension of this this cylinder, and we can determine the central frequency of the oscillation. So this really is a just a resonator that steers the actual local oscillating frequency to the characteristic resonant frequency of this dielectric resonator. Now, for dielectric oscillators, they're typically made of barium titanate, and I don't know about the exact material used for this one, because barium titanate usually it's a little bit whitish color, so I'm not sure exactly what the material is used here. But nevertheless, that's the local oscillator here. And as you can see, following the signal path here, you will see that it passes through some the microstrip the filter. So this is actually a low-pass filter here. And then it split, the signal splits into 2 paths. One goes through here, it goes to the antenna. And later we'll see the antenna side. And the other side actually goes to this another transistor, which is actually the mixer. So even though you see that these 2 sides are shorted, this is actually an LC component on the PCB trace, because of the operating frequency is extremely high. So we have a lot of components actually can be replaced by the trace, specific trace shape. And so the mixer output then, as you can see, passes another filter, and it goes to the IF output on the PCB here. So this is a extremely elegant design. And before I flip this board over, you can see that all these ground planes are actually heavily stitched. So this is to make sure that the impedance is very low, and also so that the signals do not pass this barrier. So that's the design here. And if you notice, actually the antenna output and the antenna input, they are actually not directly connected to the antenna. So when I flip it over, you'll see that this is actually, there's a slot in the middle. I'm not sure if you can see from this angle, but that's actually where the coupling is happening. So if I flip this over, you will see this is antenna, and actually it's glued onto the ground plane. So if I just peel it off, you'll see that there's no physical connection. So this is the antenna piece, and basically the signal again is coupled in through these 2 traces at the back end of the antenna. And you can see here is our ground plane, except for these 2 slots cut open for the coupling of the antenna. So which is what we saw earlier. And that 2 corresponds to the features here and here. So basically, in fact, we have more than just 5 passive components. I mean, sorry, 1, 2, 3 passive components. In fact, a lot of the traces serve as passive LC filter and impedance matching features. Again, this layout is extremely similar to what we had here on this. Let me just zoom out. Well, actually, right now I have the macro lens on, so I can't zoom it out. But you can see that's extremely similar to what we had on the photo for this HBM 100 module. And so I wonder if they copied directly from this design. In fact, you can see the feature right here versus the feature right here. So they're almost identical, including some of these filter designs actually. So if I just move it up a little bit, you'll see that some of the filter designs here is also identical to what we have on this board. And so clearly, I'm almost 100% sure that this Chinese module actually copied from at least some of the original designs that we have. So just a little bit more information on the dielectric resonator-based RF oscillator used here. As mentioned earlier, there's no direct connection between the resonator cylinder and oscillator circuitry. So you might wonder, how does this actually work? So as it turned out, although dielectric resonator behaves very similar to a metal waveguide, the major difference is that the electromagnetic fields actually exist outside this dielectric resonator material during operation, whereas for a metal waveguide, the field outside is 0. So in the dielectric resonator case, the field is actually coupled into the oscillator circuit via these features on the PCB trace. And due to its extremely high Q factor, the oscillation frequency is tuned to that of the characteristic resonant frequency of the dielectric resonator cylinder. So like a waveguide, the supported resonate mode inside the resonator is determined by the dimension of the cylinder. But since the field outside the cylinder is actually not 0, the resonant frequency is also affected by the electromagnetic field outside. So this is actually, for example, we have this metal shielding. This would affect the resonant frequency quite a bit. And if you noticed, we have actually this protruding metal piece here that actually it's hovering directly over the dielectric oscillator, or resonator, sorry. And that is used to fine-tune the resonant frequency. So actually, if you poke through this, actually I can just, so you can see that this is actually a screw back in behind this label. So there's a screw you can use to turn this pin up and down a little bit, determining on the exact resonant frequency you need. Before I finish up this video, I just want to do a measurement on this dielectric resonator used here, because in theory we can actually determine the microwave resonant frequency by just measuring the resonator. Of course, as I mentioned earlier, in this case, because it also has a metal shielding outside, the actual frequency calculation is very difficult and is beyond the scope of this video. But nevertheless, just based on the dimension of this resonator, we can actually get a rough idea of what the resonant frequency is. So here, let's do some measurement. So here's some information I took directly from the Wikipedia page. And the equation here shows how to calculate the resonant frequency of this dielectric resonator. And as you can see, it's purely based on the geometric feature of that resonator. Here is your diameter, actually not diameter, the radius of the cylinder, and the length, which is the height of the cylinder. And also we have the relative permittivity of the material. So in this case, it's between 30 and 50, which we have no way of knowing the exact permittivity of this material, but we can, just use some ballpark figure to approximate. So let's give it a let's measure it, and we will do the calculation afterwards. So here, let's see the diameter. It's well, it's a little bit hard to measure, but it's between okay, so let's just call it 4.96. Okay, so let me write it down. So remember 4.96, and so the A here would be equal to 2.48. Okay, because A is half of the D. So now the height of this, sorry, I'll show you the number afterwards. It's a little bit hard. It's between 2. Okay, so let's just call it. Well, it's actually less than this, but let's just call it 3 because you know, it varies a little bit, depends on how hard I press it against the surface. So let's call it 3. So H is 3. So now the equation comes, and let's choose this epsilon to be 40, so that, you know, just in the middle of the range. So the F would equal to 34 over 2.48 times square root of 40, and so the A would be 2.48 over 3 plus 3.45. So let's take out our calculator to see roughly what the resonant frequency is. So as I mentioned earlier, this is gonna only be a very crude approximation. So let's see, 34 divided by 2.48 divided by the square root of 40 times, in parentheses, 2.48 over 3 plus 3.45 parentheses. So as you can see, our calculation comes up with the number that is 9.27 gigahertz. And this is a little, you know, actually it's about 1 gigahertz less than what the actual operating frequency was that we observed. But as I mentioned, that the cavity outside this resonator also affects the frequency. Also, this tuning screw also affects the oscillating frequency. So anyway, so I hope you learned something new today, and also hope you enjoyed the teardown video. I will put more information on my website for the material that I covered today. If you enjoyed the video, please give it a big thumbs up, and do remember to subscribe, share, and I will catch up with you next time.